Our first speaker is Laszlo KINDRAT from XMOS, and he will be talking about performing inference on binarized neural networks with xcore.ai. You have the stage, Laszlo. Thank you.
Thank you, Boris, and thank you for the organizers for the opportunity to present here. And today I'm going to talk about binarized neural networks on XMOS's new chip, xcore.ai. And for those of you who don't know us, XMOS is a fabless semiconductor company based in Bristol in the UK. And we have partnered with Plumerai, a deep learning startup based in London and Amsterdam. And they are providing Larq, among other things, which is a platform to train binarized neural networks. And in this talk, I'm going to talk about some of the results we had porting their inference platform onto our chip, and in particular, Andrew Stanford, Jason, and Adam Hillier from Plumerai have contributed significantly along with the rest of the team. So to start off, let's talk a little bit about why we want to consider binarized neural networks. Though some of the talks today already discussed this in detail. So these neural networks have weights and activations, which are constrained to plus and minus 1, which means that you have a huge potential for reducing memory footprint, both of your model and your trained weights and biases, as well as the activations. It also comes with the benefit of enabling you to use simpler and faster hardware, since if your weights and activations are plus and minus 1, that means multiplication becomes an XNOR operation, and accumulation becomes a pop count. Furthermore, this allows you to have hardware that is also lower power. And I believe one of the earlier talks today have discussed this. So what else do you need to be able to use these? Well, you need a good training framework. And that's where Plumerai enters the picture. They have been developing Larq, which is a very simple to use extension to TensorFlow and Keras. And it allows you to train binarized neural network models really the same way that you would train any other model in TensorFlow. And what XMOS brings to the table is an easy solution for deploying these models that you trained on our xcore.ai MCUs. Now you can train your own model if you want to, or you can take one of the pre-trained models that Plumerai offers, and these models have been pre-trained on public and proprietary datasets for common tinyML tests. If you're interested to learn more about BNNs in general, I recommend you check out the previous tinyML webinar from a couple of months ago by Plumerai. You can see the link on the bottom of the screen. So if you were to work with us and try to deploy one of these models, actually it's fairly simple. You start on the left with in one of the frameworks, either TensorFlow or, as I mentioned, Larq, which is a simple extension of it. And you can have a trained floating point model, which then you post-training quantize. Or if you want to use BNNs, you would binarization-aware train them using Larq. Then you use the TensorFlow Lite converter, or very similarly, the Larq compute engine converter, and you end up with the TensorFlow Lite model, for which we provide an optimizer, which is a sort of pre-compilation tool that makes it very efficient on our platform. And our platform uses the TensorFlow Lite for microcontrollers backend, which you might be familiar with. And of course, we provide fast kernels for executing the most compute-heavy operations like convolutions, etc. So why is xcore a good platform for executing BNNs? And to give you an idea, I want to illustrate a little piece of our hardware. So xcore.ai, it's a microcontroller, but it features a really wide 256-bit wide vector unit. And this vector unit has single cycle memory access, which is going to be important when we're trying to increase arithmetic density or utilization. This vector unit provides support for multiple different quantizations, including signed 8 and 16 and 32-bit. And of course, there's a binarized mode as well. And one interesting difference compared to other RISC architectures is that most instructions in this vector unit perform a load from memory as well as an arithmetic operation. And the perfect example of this is illustrated on the left here, what we call VL-MAC-R instruction, which performs a vector load, a multiply, accumulate, and a reduce. So in effect, what happens here is you have a piece of data somewhere in memory. You have a register which is preloaded with a set of weights, and in a single instruction, that memory address is accessed, and the dot product between these two is calculated and accumulated onto a rotating buffer. And because of this rotating buffer, you actually fairly rarely have to write the result into memory. And this means that you can have these really long sequences of VL-MAC-R or VL-MAC-R1 in binarized neural network instructions. And this allows you to have really high arithmetic density. And what really high means you can see on this slide. So on the left and in blue, you can see the scale of binarized arithmetic density. And on the right, you can see it on the in orange color, the signed int8 arithmetic density. And what we have done is we measured this for a couple of different sizes of convolutions and compared the two. And what you can see is, indeed, when you go from a signed 8-bit to binary, you get roughly 8 times higher arithmetic density, or 8 times as many max per second, which kind of makes sense since your weights and your activations went from 8 bits to 1 bit. And these efficiency numbers are largely independent of the output image size, both spatially and in terms of its depth. So of course there is a catch, and that is that binarization can affect accuracy, so you have to mitigate that. And one way you mitigate it is by slightly increasing the number of weights in your model. Now, since the weights and the activations have a reduced memory footprint, right? They went from 8 bits or 32 to 1 bit. You still have a net gain there, but you may have to increase these slightly. The second thing that's often necessary is to slightly modify the neural network architecture. And of course, there are specific neural network architectures that have been designed for binarized operators. The third thing that you can do is to mix binarized with higher precision layers or higher precision operations. This is almost always necessary in the beginning and the end of the networks. The point here really is that if you use BNNs, or if part of your model is binarized, it allows you to have a different performance accuracy trade-off. You can vary which part of your model is binarized and which part is quantized 8-bit. And using Larq, actually, you can quantization-aware train both of these at the same time. So what we did to try to measure performance on our platform is we took the openly available MobileNet V1 model from the TensorFlow Lite person detection example, and we ran it on our platform xcore.ai, as well as a couple of different Cortex M7 and M4 chips. And you can see these here. These are our baseline in the squares. And what you can see is already xcore.ai is significantly faster than these. However, these models are int8 quantized, so these are not binarized at all. And Plumerai have developed a proprietary binarized neural network architecture called QuickNet Tiny. And these are very heavily binarized. Most of them have more than 95% of their weights binarized. And they have been trained, both of these, on the visual wake words data set for classification. And you can see the performance numbers here. And what's really interesting is that we took these models, these QuickNet Tiny models, with several different hyperparameters and different input sizes, and compared them to Raspberry Pi 4B, which is it features a significantly larger applications processor. So a chip from a completely different size and power and price point, of course. And xcore.ai is pretty much in the same league with it. It's just slightly slower. However, as I said, it's a much larger chip, the Cortex-A that's running in the Raspberry Pi 4B. Most of these models actually fit in internal memory on xcore.ai. The larger ones, which require a significant amount of memory for runtime, do require some external memory, which makes them slightly slower and a little bit higher cost. However, they're still well within the accessible range of a chip like this. So finally, I want to point out that we have been looking at several different variations of this QuickNet Tiny architecture, and we did a large model search where we varied the number of parameters, the depth of the different layers, and what we found was a clear trend in terms of gains if you increase the number of parameters in your model. It turned out that increasing that didn't really help much. So even though on this image you can see models which were not fully trained, so probably if you fully train them, you will get a little bit higher accuracy. But what you can also see is smaller models tend to perform just as well as larger ones. And this is an indication that probably we should be benchmarking on more complicated problems. And indeed, we are working on this. And I do want to mention that we have a white paper coming out later, where we're going to have some benchmarks for more complicated classification as well as object detection problems. So with that, I'd like to thank you for your attention. And if you're interested in learning more about us and Plumerai, please visit our websites. And I also want to mention that